this video, we're going to be learning about how the atomic theory has evolved over time. The learning outcome here is to describe the evolution of the atomic theory. But rather than focusing on names and dates, I'd like you to focus on how were experimental observations made and what data was gathered from those observations, and more importantly, how were those results interpreted to allow for the atomic theory to be revised and refined further. So our first evolutionary step in the atomic model from atomic theory was done in 1897. So remember, John Dalton was 1807, and he said that each element was composed of tiny indestructible particles called atoms. Now scientists are starting to learn that there's things that are inside the atoms. And so in J.J. Thomson's model, he discovered that there were electrons, and then he proposed a new model called the Plum pudding model. So in this first evolutionary step, we're learning for the first time that there are things within atoms. Atoms are the smallest building block of each element because atoms are the smallest building block that retain the properties of that element. Once we break it down further, these individual subatomic particles do not retain the properties of the element. So let's talk about J.J. Thomson's work and how he discovered the electron. So in 1897, J.J. Thomson was working with cathode ray tubes. Cathode ray tubes involve an evacuated glass ampule with electrodes. And you can see here that there's a cathode and an anode as part of the electric circuit here. When the cathode and anode are applied with high voltage, a beam was seen shooting across from the cathode towards the anode. This is much in the way a like neon light bulb works. But anyway, this beam here, they knew came from the cathode and it shot towards the anode. And so they called them cathode rays because they were originating from the cathode. They didn't understand at the time what this beam was. And so what J.J. Thomson did is he made a small slit in the anode so that some of this cathode ray would pass straight through, and then he could play with it. And so in this part of the tube, he lined up some magnets and also a battery so that he could apply an electric field across this. And so then he was playing with electric fields and magnetic fields and seeing the effects on this cathode ray. And so he could see where the beam was because there was a coating over here that would glow when hit by this cathode ray. By applying this electric field here, and he knew which terminal was positively charged, he knew that this cathode ray was attracted to the positively charged plate. Through some careful calculations about what angle this deflected with the strength of the electric field, he was able to calculate the mass to charge ratio of the particles composing the cathode ray. We now know that those particles that make up the cathode ray we call them electrons. He didn't call them electrons, but we call them electrons. Cathode ray tubes have lots of different applications, but CRT stands for cathode ray tube. And so if you've ever seen an older television, which is a CRT television, the reason why these are so deep is because there was a cathode and an anode back here shooting a beam of electrons towards the screen. And so if you think about it, J.J. Thomson was an early pioneer in this technology because the screen would be like this stuff over here lighting up as the electrons hit it. So let's talk about how J.J. Thomson was able to draw conclusions based on what he found out. In order to do that, we have to take a back step to show what they already knew about the structure, about charges and how charges were attracted to one another. So scientists already knew that there are positive charges and there are negative charges that just exist. They know that opposite charges attract one another, and that if you take a positive thing and you put it with a negative thing, then overall it becomes neutral with no net charge. So they opposite charges cancel each other out. Opposite charges are attracted to one another, and like charges repel one another. So you can see that these two are moving towards each other, and these are moving away from each other. So opposite charges attract, like charges repel. And also, scientists understand that the magnitude of the charge does increase as the amount of charge increases. So you see that each of these has 3 positive charges inside, and the arrows are much bigger than when there's only 1 positive charge inside. So more positive charge, more repulsion, or more attraction if they're oppositely charged. And then it also scales with distance. And so these are farther apart, and so the arrows are not as big as these which are close together, and now they are much bigger arrows because they were closer together. So based on J.J. Thomson's observations that it was attracted to the positively charged plate, then he knew that since opposite charges attract, the beam must be negatively charged. So he concluded that whatever was in this cathode ray must be negatively charged. He was also able to calculate the mass of the electron, and he knew that that was much less than the mass of a hydrogen atom. And he knew that the mass to charge ratio was the same regardless of which element was used as the cathode material. And so this same beam was coming from all atoms, not just a specific metal. It wasn't specific to the element, it was just generic across all elements. And so therefore he concluded that it must be a fundamental subatomic particle, meaning smaller than atom size, that belongs to all atoms. And so he revised this atomic model to include that there is an actual physical negatively charged particle inside the atom. So that overall it would be neutral, and so this cloud was positive cloud with embedded negatively charged bits inside. So it kind of resembled an English dessert known as plum pudding, which has bits of fruit floating randomly inside. And so this is known as the plum pudding model of the atom. In 1906, Robert Millikan had done an oil drop experiment. And so if you look at the years here, the plum pudding model was proposed in 1904, and the oil drop experiment was in 1906. So just a couple years later. But the Robert Millikan in 1906, he took an oil mist, very fine mist here, hit it with a whole bunch of x-rays to produce a charge on the oil mist droplets, and then allowed them to fall based on gravity. And since they were charged, he could apply an electric field and try to counteract the force of gravity on these droplets and keep them suspended in space. From doing some very, very careful calculations, he was able to calculate the mass of the droplets by allowing them to fall without an electric field and how long it took them to fall just based on gravity. And he was able to calculate the charge on the droplets based on how much electric field was necessary to keep them suspended in space. And so from that, he was able to calculate this fundamental charge, which is given the symbol E. And so you can notice here that it is a positive constant. This is a constant known as the fundamental charge. And so if you are thinking right now, I know that electrons are negative charged and protons are positively charged, you might have also seen an E after these. And electrons have -1 E. That means -1 times 1.602 times 10 to the -19th coulombs. This unit here, I'm not sure if I'm spelling that right, but anyway, that's the unit of coulombs. And that's one of our units. But protons are +1 of this value. So this is a fundamental constant, and we oftentimes just refer to electrons as -1 and +1. And this is what the magnitude is when measured in coulombs. But as with all things, J.J. Thomson's work was furthered by his student Rutherford. So Rutherford was J.J. Thomson's student, and he set out to he was a big fan of this atomic model. Electrons were very controversial at the time. People didn't want to wholeheartedly buy into them, and so Rutherford set out to design an experiment to show that yes, there were electrons, and it would verify J.J. Thomson's model of the atom a bit more. So Ernest Rutherford, he predicted that he could, okay, well, let's talk about his experimental setup. This is known as the gold foil experiment. And there's a radioactive isotope in here known as radium. Radium is a alpha decayer. Alpha particles, we now understand, are helium nuclei. And so they are positively charged. At the time, they did know that they were positively charged, but he didn't really know what they were exactly. So this beam of alpha particles was kind of directed this way by only having a small outlet for them. And so this beam of alpha particles was shot at gold foil, a very thin sheet of gold foil. And then he had a detector set up going around that could help him identify where the alpha particles ended up. And so, based on this plum pudding model of the atom, he expected this beam of positive charges that was going super fast to mostly just pass straight through because the atoms were overall negative. He did set the detector up, or the atoms were overall neutral. Sorry, I misspoke earlier. He did set up the detector going around in a full circle because he thought, okay, well, if this particle gets too close to one of these electrons, its path will be bent a little bit because it will be attracted to some electrons. And so he expected most things to go straight through and then some to be bent slightly. But that wasn't what he observed. Instead, he observed that, yes, most particles did go straight through, and so that part he did observe. But what confused him for a while was that some alpha particles were deflected at very sharp angles. And so some bounced like almost straight backwards, and others were bent very severely. And so, like, even though they were all going in here, some came pretty much straight backwards. And so he was like, what the heck? And so he knew that these were positively charged, and the only thing that could repel a positive charge is another positive charge thing. And so he concluded that all of the positive charge for an atom must be in the center of the atom. That way it would be massive enough to cause the alpha particles to pretty much bounce straight backwards. So he put all of the positive charge in the center of the atomic model. And then, since most of the alpha particles did pass straight through, he concluded that most of the volume of an atom must be empty space. Through some further experimentation, Rutherford and his student Chadwick also discovered that there are neutrons in the nucleus as well as the protons, the positive charged objects. And so overall, the nuclear model of the atom was born. And so there are 3 subatomic particles to an atom. There are protons and neutrons in the nucleus of the atom, which is in the center, and that accounts for most of the mass of the atom. And then this electrons are in some kind of cloud around nucleus. And it's mostly empty space because the electrons don't occupy very much room. But protons and neutrons in the center, mostly empty space, some random electrons in there. And so it is mostly empty space. The diameter of an atom, so this diameter is about 10 to the minus 10 meters. And so it's a really, really tiny, look how small that exponent is. So it's a really tiny object. And the nucleus is about 1 in 10 to the minus 14. We'll just say 10 to the minus 14. So it's much, much, much smaller than the overall atomic size. But that's where most of the mass is. So if you think about like a blueberry or a marble in the center of a football field, but then that blueberry or that marble being super duper duper heavy compared to the whole football stadium, it's kind of mind-blowing. So this table kind of summarizes the mass of each subatomic particle and the mass in grams and the mass in atomic mass units, and their fundamental charge. And you can see that the mass in kilograms, all of these are written with the power of 10 to the minus 27, so that you can kind of compare how much mass the proton and neutron contribute to the mass of an atom compared to the mass of an electron. This is way smaller. So it would take 1,838 electrons to equal the mass of 1 proton. So the mass of an electron is way, way, way less. And so here we have the masses of protons and neutrons being about 1 atomic mass unit-ish. And protons are positively charged, neutrons are neutral, and electrons are negatively charged. So there are other atomic models that we will be exploring in the upcoming units, including Bohr's model, which was developed in 1913, and the quantum mechanical model, which had contributions from Erwin Schrödinger and Heisenberg. And that's our modern model of the atomic atom. And so we will be evolving the atom even further in the upcoming units. And I always find this interesting, but it's often very disconnecting to read these names in the textbook and really have no sense of connection with them. But really, you and I are connected to them. All of these textbook names. So there's a website called academictree.org, and it shows who got their PhD from who. And so here I am. I found myself on this website, and I got my PhD from Susan Koslerich, who has worked with John Corbett, who worked with Norman Gregory, who worked with this person who worked for Linus Pauling, who is famous in his own right. And Susan actually had an autograph from Linus Pauling. They met each other. Linus Pauling worked for Niels Bohr and Erwin Schrödinger, who helped develop those atomic models that we have yet to talk about. And then Niels Bohr and Schrödinger, well, Niels Bohr in particular, was connected with J.J. Thomson and Ernest Rutherford. So these are those big textbook name people that are very important in this chapter. And so that's 1 degree, 2 degree, 3, 4, 5, 6 degrees of separation between me and Niels Bohr. And that would make 7 degrees of separation between you and Niels Bohr. So in summary, the scientific method has advanced our knowledge of science in general and the structure of matter. And we've seen our knowledge of the atomic model get modified and evolve over time to accept new experimental observations. All matter is composed out of atoms, and atoms have a nucleus in the center containing a proton and neutron and surrounded by electrons. Most of the mass is in the nucleus, and the volume is in the electrons cloud.